So in this, we have different flag bits. The status register is something like it will get different flags at different time. Got it now? So here, different flags means it will, the bits of that register will be updated by ALU operation or memory operation.
Yes, sir.
Let
Yes,
us
sir.
say we are performing a calculation, addition, there we get a carry, then the carry bit will be set to 1. Right now, we perform an operation, a subtraction or something like that, we get a 0 as a result, this 0 flag will be set to 1. Right, we'll study this PD and T naught. They are again some sort of status. This RP naught, RP1, these two bits are used for reflecting to make the bank selection. When you want to select a particular bank, totally I told 4 bank naught, bank 1, bank 2, bank 3. When you want to select a particular bank, you have to code here. Let us say if I want to select bank 1, I will set this bit to 0, 1, RP1 0, RP0 1, so that I will be selecting bank 1. Understood? So it is like that. When we are in different banks, when we try to access status, if we have different address, that means if we have a fixed address for status, it will be very tricky. Every time when we want to make any changes, when we make a bank change, we have to come to bank not first and then only we can make the bank selection. That is very tedious. That's why what they did is they simply created a different, what they can say is a different shadow. Physically, it is one register. Its shadow exists in nearly 4 banks: bank naught, bank 1, bank 2, bank 3. And every bank has their own address to access status. Right. Here it is 3, in another bank it is 83, like that. But when you store or when you read anything from this register, that will affect a single location only, single register location only in the memory. Do you understand what I'm trying to say?
Yes, sir. The question, sir, I have one question. Like, why they have segregated into different banks?
Why don't we have a single bank?
Means what is the purpose of?
I think that may be the reason behind the chip design. In the data sheet, it is not explained. Maybe there are some programmatical reason as well that we have to explore. As of now, I'm not aware. So they have that design like that. But in the past, I worked with the DSP, I worked with the digital signal controllers. In every microprocessor as well as microcontroller, I had seen this concept. When it comes to RAM, they will segregate them into different banks.
Okay.
This is a common ideology that exists in chip manufacturers. Obviously, there will be a valid reason, but I didn't raise this question, or that question is not answered in any data sheet.
Okay.
What we studied is, okay, we have a bank, so you have to access the bank like this. But why we have the banks, different banks, that questions, maybe I failed to raise that questions, but it is also, it is not clarified in any data sheet. I had studied the data sheet in the past, but they did say, oh, these are because of this we created the different banks. That's not explained. Maybe some valid reason will be there that we have to explore. Maybe the chip design course or something like that. If we do our research in that area, we may get some idea.
Okay.
Right.
And this PCL and all, these are CPU register, right, sir? Why they are in special function register? Uh, they are mentioned in.
Okay, brilliant. So the PCL program counter, see, but the program counter should also have some memory location, no? Right. So CPU will have the circuitry for logical operation, but it won't have a location. That is, within that itself, there won't be any location to store something. They have to get the support of RAM. That is available in microcontroller within the chip itself. See, in microcontroller, microprocessor also, PCL will be there in on chip. Yes, as you told, they are CPU registered, so it will be part of the CPU. We no need to go for outside. We don't need to go to RAM or something like that. They are part of the chip. Yes, in microcontrollers also it is part of the chips, but we have other registers as well, like timer not register, port B register, port C registers. So they are also there. When they want to keep all these registers in the microcontroller together, you are seeing like why this is a CPU register only, no, why it is here. Yes, in microcontroller also it will have a bank not bank 2, bank 1. There they will allot one location for program counter. Whenever your CPU computes something, it will use the address from this particular memory location only, maybe the register only. That is part of the microprocessor. Here, yes, it is part of the microcontroller, as well as they have an additional registers. So for you, it appears like why in the location of peripheral register we see program counter. You are looking like that
Okay.
because in microprocessor there won't be timer not and some sort of port register. In those things won't be there, right? Only registers related to the microprocessor will be available. That's why you feel a strange. Actually, in microprocessor also, they have a register location in the memory of that microprocessor. There they used to store the program counter value. We need some location to keep the data. Now, address is also a data. To
Yes.
keep that, we need a location, right? In microcontroller, we have that with other registers too. In microprocessor, it will be very few registers, that not this much big list,
Okay.
right? So then indirect data memory address pointer. So when you want to increment this FSR, you have to use this particular thing, I believe. Indirect, initially you have to store something in FSR, and then using INDF addressing location uses the content of FSR address memory, not physical register. Okay, you store a value in FSR and then use INDF to modify it, increment it, decrement it, something like that. Fifth location is port A, port B, port C, port D, up to from memory location 5 to 9 we have port registers. I told in instrument cluster we have annunciator, telltale annunciator, right? So in order to make those telltale annunciator to glow, we have to supply high or low voltage to that LED circuitry. That is what I discussed right now. So above that LED, they will have an annunciator, a image, a transparent image. When the LED glows, it will look for us, it will appear like a image is glowing. Maybe a seat belt, check engine, tire pressure, something like that, right now. So to give high or low voltage to those pins programmatically based on our need, we need some port pins in our microcontroller. Yes, no. So those LEDs are going to get input from the controller. Controller, what is the control signal given by the controller? Active high or active low. In some design, circuit design, if you supply active low, the LED will glow. In some circuit design, when you give active high, the LED will glow. It depends on the design, board design. Agree. So to give high or low voltage to that particular LED, we need some sort of control pins in microcontroller right now. Yes or no?
Yes, sir.
So those control pins are driven. Physically, there will be a pin, digital I/O pin in the microcontroller. So totally, how many ports we have? 5 ports we have. No, you can immediately calculate 5 8s 40 pins will be there. No, some of the ports have complete because each port has 8 bit, 1 byte right now, 8 pins, right? But actually, physically, there won't be all 8 pins are available for all ports. Maybe port A, port B, port C can have all pins available for control. For other ports, port D, port E may have a minimal ports. Actually, here they have explained very in detail. In port A, we have only 6 pins available for to send the control signals. In port B, C, and D, we have 8 pins. All 8 pins are available. Understood? And then in port E, only 3 pins are available. In total, so 6, 24 plus 6, 30, 30 plus 3, 33 pins are available for controlling different digital circuitry which requires a active high or active low. Yes or no?
Yes, sir. Sir, can you give one example use case? For example, if we are just giving a digital high for one of the LED, so just to make on. So in that time, first we are going to configure, we are going to assign some value to the port, this one, and then we are giving the output pin, right, sir?
Okay, let me give that example.
How the flow works.
Okay, yeah. First of all, these registers, these registers are configurable. That means can be we can multiplex them. The port A pin can also be used as output pin, can also be used as input pin. So we can receive digital input as well as we can send digital output. Both are possible. If that is the case, first of all, we have to define whether we are going to use that as a input pin or output pin. Any pin in that particular register, right? Let's say maybe there is a register called TRIS, TRIS, TRIS A, TRIS B, TRIS C, TRIS D, TRIS E, like that. For each port, they have one dedicated register. These register will define the direction of data, whether you are going to receive an input from a particular pin or you are going to send the output using that particular pin. Actually, the register is to say, actually it says the direction of that is data direction of port A register. Port A register, a port A register is associated with some pins. Let me explain in this way. I have a port A register right now. Port A register is how many bits it is? Totally 8 bits, right? 6 bits, totally 6 bits. So these 6 bits are associated with 6 different pins in the microcontroller. So here is a microcontroller. Microcontroller has 6 pins. 1, 2. These are only port A pins I am talking.
Okay.
4, 5, 6. But the register that they are saying in the data sheet is port A 1 byte in size. Port A size is 1 byte, right now? 1 byte means how many bits? 8 bits, right? So we need to have 8 pins only, no? But we have only 6 pins. So from the port A bits, only least 6 bits are associated with this pins, with these pins. This port A will have how many bits? 6 bits I told. So let me group them in 4 bits as a 2 nibble. That is actually this is LSB, this is MSB. So each one bit in this particular register is associated with one pin. One bit is associated with one pin. The second bit is associated with second pin. Third bit is associated with third pin. So all 6 bits are associated with 6 pins. Agree?
Yes,
Clear?
sir.
Okay, brilliant. Now these pins can accept the input as well as we can use them as output pins. We can also receive input from pins. For example, if I make this as an input pin, if I supply an active high, automatically the bit not in the port A will become 1. If I configure that as an input pin.
Okay.
When I give active high here, automatically port A bit not will become 1. If I configure that as an input. Now the question is how to configure a particular pin as input or output. For that, every port register is associated with a control register, which is a data direction register. Tris A, Tris B, Tris C, Tris D, like that. What this register will do? Let's say if I say Tris A, if I load Tris A with the value 3, let us say I load Tris A value to 3. What it really means Tris A value 3 means totally Tris A has 8 bits right now. So 8 bits. So I can write 8 bits like this. Right. But at least 2 bits are 1. Now the Tris A is having this value. But among these 8 bits, only 6 bits are processed, 2 bits are don't care. Forget about them. Because they are not associated with any pin. Remaining this 6 bits that we have in the Tris A, if I set that particular bit value to 1, I consider that pin as input. Which pin? Port A pin not become input if I set port not Tris A bit not to 1. Port A bit not becomes input when I set Tris A bit not to 1, which means that when I make the Tris A to 1, this port A will get the input from outside world and digitize it either 0 or 1 based on the input. Do you understand?
Yes, sir. So each port will be handling some pins, and to make active high and low, we will use port register, and to make it input or output, we use this Tris A register. Right, sir?
For every microcontroller, the name will be little bit different. Tris A, DIR, like that. But at the end of the day, all are going to do the same task. They will associate port register value to pins. Then they will tell the direction of those port register bits, whether is it a output pin or a input pin. That to handle that, they will have another register called data direction register or TRIS registers if in case of PIC controller. Got it now?
Yes, sir.
Like port A, port B, port C, everyone will have tris A, tris B, tris C like that. Let me take an example of real world thing. I want to, when there is a failure in the engine, I want to make the check engine telltale to glow. For that, what I will do, I connected pin knot to a register, and then I connected a LED in inverted way. I supplied that to, maybe I think I have to have the resistor here to 5 volt. Right? By default, pin will be in high impedance state, so that high voltage will come. So here also 5 voltage, here also 5 voltage. LED, there is no voltage difference, so LED won't glow. Now, here I have a image which is representing a check engine above this. I think you assume this is a check engine. It is not appropriate, but anyhow. So I have an image on this. Whenever this LED glows, this annunciator will glow in the cluster. That means meter. Okay. I have to make this LED to glow when there is a fault in engine. I come to know due to sensor value, so there is a fault in the check engine. What I will do, first I will set my tris A value, because this is byte not, no, tris A value to bit not to 0. So let's say I can make like this. I set my tris A value to 0 so that all port A bits becomes output pins.
0 means output, it is default, or it is microcontroller specific?
Microcontroller specific. In big controller, I think most of the controllers that I work with, 8051 and big controller, everything, 0 means output, 1 means input. They follow the same, some sort of uniformity.
Okay.
Right. So let's say I made it to tris A bits to 0, so that this particular pin become output first. After that, I will set the value port A is equivalent to, I have to make that bit to 0. Only then it will become low. As it becomes 0, automatically LED will try to glow. So what I have to do, I can say port A equal to, I just write C program here, port A and with F0x E. Can I do like that? So all bits are made 1 except least bit. Let us say the port A is having initially some value, some let's say it is having even FF. All bits are set to 1. Right. If I make AND it with the FE, all other bits will have their value as such. Whatever the value they are currently in, that will come. That means 1, 1, 1, 1, and these bits also 1, 1, 1. But the least bit, the bit not will become 0. Agree? Yes or no? Come on. When I AND
Yes, sir. Yes, sir.
with FE, I will get least bit in that particular register will set to 0. As it set to 0, microcontroller will make this pin to active low. As it goes to 0 voltage from high impedance, the voltage flow will happen from 5 volt supply or source. We get the voltage flow in this diode LED. It will glow. The moment it glows, automatically the annunciator will glow in the cluster. So this is a simple use case. Understood?
Yes,
This
sir.
is how they will do the port programming.
Okay.
For each fault that we have in the module, we can dedicate one pin
Okay.
right now.
So, yes, sir. For simple LED uh, program also, we need to first configure these two registers, and then we need to give the.
Yeah, see, even simple LED control program, we have to do this much of things.
Yes.